Hello everyone, welcome to our video today where we're talking about Physics Chapter 6, Circuits. Now there is a lot of information to go over in this chapter, so there's definitely a lot of questions that you can find, practice questions that incorporate so many of these things and so many details. So I would definitely do some of those. I didn't have the board space or the time to go through problems, but hopefully this gives you the equations and the basic concepts that you need to apply to those problems. So without further ado, let's get started. Okay, so we have the basics of conductivity, which I'm assuming at this point you know what conductivity is. You know that metals are good conductors. There are metallic conductors and electrolytic conductors. The electrolytic conductors are really based on a solution, and metallic obviously with a metal. So that is how, you know, the wires in our circuit that we are going to talk about, that is how, you know, the charge is conducted, because it uses a good conductor. Okay, so current is induced by voltage across conductors. So the current is relative to the positive charge flow, even though it's the electrons that are actually moving. If you watch any, you know, other videos on YouTube about that, I'm sure that's one of the first things they tell you. And I think it's had to do with that electrons were discovered long after this theory was kind of in the works. But yeah, it's a little counterintuitive of how we define the current. But the equation for current, I wrote it nice and big here, is represented by I. So the current is I equals Q over T, which is Q is the charge and T is the time. So the units for this equation is amps is the current, coulombs is Q, and seconds is T. So another thing we need to consider when we're talking about circuits is voltage. And voltage is the difference in potential between the positive and the negative terminal, which we're going to talk about in a moment, but it's the difference in that potential, okay? That's how you get a voltage. And the voltage units are volts or joules per coulomb. Okay, next let's talk about resistance. So resistance is an object's opposition to the flow of charge through it. Basically, a good conductor has low resistance, right? And a bad conductor has high resistance. It makes it harder for the charge to flow through it. So we have a couple of tying all these things together, we get Ohm's law. And what Ohm's law is, it says that V equals IR, which means the voltage equals the current times the resistance. And so if we look at the graph here, we can see the voltage on this axis, the current on the x-axis, and this slope here is actually defined by R. So you can look at this equation, and a lot of questions that I've seen has been about relationships. So if you increase this, and if you increase resistance, and you know, I stays constant, what happens to the voltage, or things like that. So just be familiar with this equation so that you can understand the relationships that it kind of entails and that you could be asked about. That's true with a lot of equations on the MCAT, to be honest. But anyways, so yes, also, yeah, just recognize that graph. So R, right, is very interesting because the resistance is actually as part of another formula here, and it's rho times L over A, where rho is the resistivity, which basically is the number representation of specific materials or substances. You'll get a number for that, okay, as rho. And area is represented by A, and length. Okay, so know that this also is going to be in meters as well. Okay, put that in terms of meters. That way when you input it in some of the other equations, it makes sense. Let's see what else we have here. Okay, so that's it for Ohm's law. So definitely know that equation and you know what the variables represent and the things that can affect the resistance value as well. Okay, so having said that, we are going to come down here for a moment and we're just going to talk about a circuit in series or in parallel. So the resistors, okay, that's what you actually call the things that you put in the circuits that have the circuits that have, you know, resistance. Those are resistors. So the resistors, we ignore the black writing for right now, but it can be placed in series. That says series. Sorry, the blue is a little faded. And parallel. So if you put it in series, which I drew over here, okay, this is in series, so it's here and here are the two resistors. That's the resistor, okay, the kind of jagged line. So in series, there's only one path for the current, and the current is the same through each resistor. That is a very important point. So write that down, highlight it, and know it. In series, the current will be the same through each resistor, okay? So that's this picture right here. And so to find the total resistance, you're going to add them up. So the resistance of the first resistor plus the resistance of the second resistor and so on, depending however many there are. But if you put these resistors in parallel, that means that the current will have multiple paths, right? And in this case, the voltage will be the same through each resistor. Now that is also important. So if we're looking at this image here that I drew, this is a circuit, a parallel. These resistors are placed in parallel, right? Multiple paths. So the current can come through here, the current can come through here, and still come back to the other side of that battery. So this is in parallel, and like I said, multiple paths, and you will get the same voltage through each of these, okay? So, how to find the total resistance in a parallel circuit, resistors in circuit, will be 1 over the total equals 1 over resistance 1 plus 1 over R2, etc. So when you do this at the end, if you actually want to know what your R total is, make sure you remember to flip it, right? Because these are all fractions. So at the end, just make sure your reporting or the answer that you click is the actual REQ value, not 1 over REQ. Okay, so let's talk about capacitors now. Okay, I think we're ready to move on. So, so you can see the top of that. There we go. Okay, so capacitors are used to store charge. They are composed of two parallel plates with a space in between or with a material in between, and we'll talk about that as well. But capacitance, okay, is represented by C, and that is K times the E constant times area over distance. And so let's talk about what this means. So the capacitance C equals K. K is the dielectric number. We're going to talk about dielectrics in a minute, but just for now, note that K is a dielectric number for if this circuit is happening in a vacuum, or if there's air between the two. Right here, we're gonna get to it. But if these are the capacitor plates here, and there's air between the two parallel plates that are not touching on your capacitor, if there's air between there, or if it's in a vacuum, then that means your K is equal to 1. Okay, you're gonna use 1. But if you have, for example, glass or another material in between your two parallel capacitor plates, that means that your K value is going to be greater than 1. I wrote that sign wrong. Others will be greater than 1. Let me fix that. Others will be greater than 1. Okay, so we're looking at, okay, let's keep going. Also, the E will be a constant. You'll be given the constant. That's just a constant there. And then also the area over distance. So the area is the area in meters of the parallel plates. And then the distance is the distance between the parallel plates, okay? So the area would just be of one of the plates, but the distance is the distance between two plates, again, meters. I like to just put everything in meters that I can because I've been tripped up a couple of times where the question has, you have to input certain numbers into these different formulas, and if you just keep it in meters all the time, you will not be confused. Okay, so, because some of them require that, so I would suggest doing that instead of waiting till the end and having to remember what you converted, what you didn't. Just change everything when you're using these equations. So the positive terminal has a higher potential. Potential is denoted by this symbol right here that you're probably going to see again. And that is in an image shown as the longer line. So here is our longer line, right? So this means this is our positive terminal of our battery, basically. And so we see that this happens. If this is our positive side, right, the longer line, we can see that on our capacitor plate, this side is positive, right? We're building up this positive charge. Now, on this side, our negative terminal has a lower potential, and that's represented by the shorter line, okay? So that's that shorter line there. Okay, so how much charge can a capacitor store at a specific potential difference? That's a very important question. That is what this capacitance basically is telling you, is how much charge the capacitor can store at a specific difference of potential. Whereas if you want to see the amount of charge that can be stored on a capacitor, you're going to use Q equals CV, where Q is the charge, C is the capacitance, right up here, the C, and V is the voltage between the plates. An important part of this also is when we're talking about the charge, is the positive charge on this side has the same magnitude, has the same absolute value as the charge on the negative side. Okay, so these are going to be equal but opposite charges on these sides. So when we're looking at this charge, we're talking specifically about the amount of positive charge on the positive plate or the negative charge on the negative plate, not the total, okay? Because like I said, they're equal, so that wouldn't work in our equation. So we're literally talking about just the amount of positive charge on the positive plate, and then the amount of negative charge on the negative plate for the charge that we're referring to in this equation. Okay, so another thing that we need to talk about is the electric field. The electric field goes from the positive to the negative plate. And that equation is V over D, voltage over distance, okay? Perfect, just some little tidbit in there. Now, if we pay attention to this black writing over here, work on a system, okay? We're going to talk about work on a system here. Is the change in potential energy of the capacitor. That could be equivalent to a couple of different equations, and you use these different equations in different instances. So let's say that the first one is half of QV, okay? It can also be written as, the change in potential energy can also be the 1/2 of CV squared. And you use this equation when the capacitor is connected to the battery. Because when the capacitor is connected to the battery, the voltage is constant. So that means you can use this because the voltage will be constant, and you can see how capacitance is affected, and therefore the potential energy. But we need this to use this equation because the voltage will be constant. Then we can also use this equation is Q squared over 2C, and you use this equation when the capacitor is disconnected from the battery, because when it's disconnected, the charge is what will remain constant, okay? At a constant voltage and an increased capacitance, that will increase the potential energy, just as a good relationship to know. And at a constant charge and an increase in capacitance, that will actually decrease the potential energy. And that is because if you look at a graph, right, we're saying the work is a change in potential energy. If we're looking at a graph that's created by both of these things, when we're looking at charge and capacitance, you're measuring the area under the graph, right, is the work. If you look at that graph, you'll see like when you kind of change the graph to say, okay, this is a higher capacitance, you can see the area shrinking under the graph or getting larger. That's, if you want to know how how these relationships really play out, go look at that in a little more detail. But what you'll see from that graph is this relationship, okay? All right, so now let's talk about dielectrics. Dielectrics is the insulating material that polarizes an electric field. So we talked about a little bit up there. We're going to talk about it in a little more detail. So as, let me just see here. Okay, so capacitance increases based on the dielectric number, okay? So it's capacitance equals K times K naught, basically. As we said, for if it's in a vacuum or air, the K value will be 1. If it's another substance, it will be more than 1. Okay. Oh yes, and how does our Q equals CV kind of react to this change in capacitance? So if you're disconnecting the battery, as we said, disconnecting the battery means that the charge will be constant. Therefore, in this equation, if Q, did I say K? I meant Q. I don't remember what I said 2 seconds ago, but let me start that over. If you're disconnected from the battery, it means Q is constant. If Q is constant and capacitance increases, that means the voltage will decrease, right, to maintain Q as a constant. I'm hoping you can see. I'm going to pick this up and come a little closer so you can see that for a second. And then the second thing there says if you're connected to the battery, Q will increase, and the capacitance also would have to increase because the voltage is what's staying constant. Okay, and that is the same kind of idea that we used when we talked about these equations. Yes, but this is just in terms of capacitance and these relationships. So what you see from a lot of the stuff we've covered today is definitely the relationships, okay? So we have 3 more things to say about this, and then we'll be done. I know this is quite a long video, but there's a lot to cover in this chapter. So power, we might also see that when we're talking about circuits. Power equals IV, right? Current times voltage. It can also equal current squared times resistance. It can also equal voltage squared over resistance. Okay, so just know that those equations as well. Measurement devices for circuits. We have voltmeter and ammeter. So the voltmeter is in volts. It measures voltage. It will be placed in parallel to the circuit. So you're not going to put the voltmeter connected to the ends and let it be part of the circuit. Okay, that is not what you do with this this voltmeter. You use it in parallel, and this has a very high, it has a high internal resistance. which is because, right, the reason that the voltmeter will have an increased internal resistance is because we don't want the current to see the voltmeter as a pathway that it could take, right? No, we want it to take the regular circuit that we have. We're just using the voltmeter as a measurement, which means that if we have a higher internal resistance of the voltmeter, then the flow will not try to use the wires of the voltmeter as a pathway. But when we're talking about an ammeter, we're talking about measuring the current that is placed in series in the circuit, and it has a decreased resistance because we want the current to pass through the ammeter so we can get an accurate measurement of the current, right? Okay, so we're on to the last thing. When we're talking about one thing I didn't mention before because we didn't talk about the capacitors yet, but now that we have, the capacitors, when they're placed in series, they have this equation right here. So it's 1 over C total equals 1 over C1 plus 1 over C2. Okay, so it's the same idea as the resistors in parallel, but this is we use this for the capacitors in series. And then for the capacitors in parallel, that is when the total capacitance equals C1 plus C2, etc. So that's just another thing I wanted to mention. I think that is everything. Yes, so hopefully that helped clear up a couple of things. I know there's a lot, as I said. But I hope you're having a good day. I hope that you're really studying and keep pushing yourself. And I know it's complicated, but you can do this. And I will see you in the next video.